All right, so your first take-home test, BC Review 12. It'll be in Canvas. It's also at the bottom of my website. Calculator permitted. Just to show you're working a separate paper, since I haven't updated that since we had iPads. So go ahead and do it on your iPad. And again, don't just show the answer, show your setup, okay? So like if you're finding the derivative of f at 4, put f prime of 4 equals, then you're welcome to use the calculator, okay? Today is Wednesday, Thursday, 10 questions. It's busy time for y'all. Let's make this due Monday at 9 a.m. I don't want to give you the whole day because I want to be able to answer questions about it in class, okay? So Monday will be what, the 32nd? It's the 32nd. No, Monday is the what? Just the 32nd, right? May 2nd. May 2nd. I think it's May 2nd. Okay. Any questions on that? Take home test. All right, number 12. Grid choice. I like the fact that we're using calculators. So thank you, Juliana. That deserves kind of a round of applause for picking a good number. All right. Now, remember that you also have access to the website on your own. I know you're watching the videos in the background. We're going to circle back to some of those, but these are all BC reviews where I have the key. There's no videos, but I show how I work them out. So there's all the stuff there. There's all the stuff that's still in the shared folder. This afternoon, I'll do the next review, and that'll be review 14 already that I've done before after school. So the AP exam is on the horizon. And as you heard Ms. Neely say earlier, space forward, both of y'all, forward. Bend the leg forward. Oh, okay. Safe. Okay, forward. Yeah, don't look at Hank. Hank, deflate the balloon. I hate to burst your balloon, deflate it, but yeah, okay, it's a distraction. Yes, Landon. That's okay. Yeah, it's okay. Question 12 is a polar curve. You have till Monday to watch the polar video. Okay. Yeah. I mean, I've assigned it, right? So thank you though, Landon. Yeah. And we'll go over it. I mean, I'll grade it. So there's an incentive for you to do that. And then we'll have another one next week that'll be due. We'll have another one next week early. I'll probably assign it Monday, and it'll be due later in the week, maybe Thursday. So we can go over it on Friday, because the AP exam for y'all is at May the 9th. May the 9th. May the 9th be with you, right? Okay, so what we're doing today in class is finishing 9.4. Okay. So remember, we're looking at special power series that are geometric series, and we can build off of them. We can manipulate expressions, kind of fun like, to find the radius and interval of convergence. And remember, if you can spot it as geometric, and you're trying to find the domain or the interval of convergence, do you have to test the endpoints? No, you don't. Geometric series. Endpoints won't work. Okay, but remember, when you take the derivative or integrate, then you have to recheck the endpoints, because if they weren't there to begin with, they may be added, or versa versa. So look at example 10. Find the power series that represents 1 over 1 minus x quantity squared, right? Centered at 0. Okay, well, it might not be obvious to you how we can use 1 over 1 minus x. Remember what that was? That was 1 plus x squared plus x cubed plus ... plus x to the n plus ... How can I just square this right here? Can I just go through and square all of these like that? I don't know how that works, right? So you might be given like a hint. If you're not intended to like reinvent the wheel using Taylor's rule, here's the hint. What is the derivative of 1 over 1 minus x? So one of the things we could do with series, infinite series, is, since they're identities, really, it's what we're saying, the left side is equal to the right side, we can take the derivative of both sides. Okay, so let's see what that happens to be. I should get rid of the squared here. There you go. Let's take the derivative of both sides with respect to x. Now, off to the side here, remember 1 over 1 minus x. You could use the Hody-High rule, but it's probably faster to write it as that, right? 1 minus x quantity to the negative first. So if I were to take the derivative off to the side of my workbench, that would be, I guess we could do it here, negative 1 times 1 minus x to the negative second. There's that negative right there. I should make it a little bit more prominent. There we go. That's what the derivative equals on that side. And what does the derivative equal? Well, I don't even know if I'm supposed to do it on the other side. Let's work straight down. That simplifies to -1 all over 1 minus x quantity squared. Oh, okay. So what do I have to do then to generate the geometric series for 1 over 1 minus x quantity squared? How can I get that from 1 over 1 minus x on the right side? I took the derivative, which gave me pretty much everything I wanted, but I'm going to be off by a negative, right? Because I need to have a -1. So really, that's just what?
Wouldn't it be positive if you have to take the derivative?
Oh, I didn't do the chain rule. Yeah, I was going to say. No chain. That was a huge mistake, because if I don't do the chain rule, I would have to multiply everything through by a negative. Boom. Anytime your inside function is something more than plain old x, you have to consider the chain rule. Okay. So that does actually make it a positive, which means, hey, guess what? It is right on the money, as Alan Jackson said, right? So all I got to do is take the derivative of both sides. So let's go ahead and do that. I'll do that over here on this line, because we want to keep working straight down. So the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x plus 3x squared. Now, if it says to write the first 4 non-zero terms, is that good? No. So we need to add one more term. Gosh, what would it be? 4x cubed, right? And then plus ... for the general term. All you got to do is do the power rule. It's n times x to the n minus 1 power, and then plus ... And putting parentheses around the n minus 1 is kind of nice. So if you clean that up, there's really not much left to do except maybe get rid of that first term. 1 plus 2x plus 3x squared plus 4x cubed. And now you can see the inherent pattern. The next term will be 5x to the 4th, so on and so forth. All right, so that gives us the series, and you probably will be given that hint. That's kind of a hard thing to come up with on your own, kind of like a trig proof. So if you're given the hint, they're expecting you to realize that. Now it says, what's the radius and interval of convergence? Well, the center is 0. When I take the derivative, I don't change the radius, do I? So what was the radius originally for our plain old generic 1 over 1 minus x function? It was 1, right? We're centered at 0, and we can go, the absolute value of that needs to be less than 1. So when I take the derivative, the radius is still 1. But I do have to check the endpoints very quickly. Okay, so what would the interval be? The IOC. It would possibly be -1 to 1 with brackets or parentheses. We're not sure which. So how do we figure out what that is? Well, you can kind of do it in your head right there. You're going to plug it into the sigma notation, which we don't even have written there. But we need the rule of sequence. We need the nth term, or the general term. So if you plug a -1 in for x right here, you get n times -1 to the n minus 1. Is -1 to the n minus 1 an alternator? Would it be? I'm just going to talk through this instead of write it down. -1, the quantity to the n minus 1 would be an alternator. Yeah. N plus 1, n minus 1. So maybe the alternating series would n then, as n goes to infinity, decrease to 0? Heck no, it doesn't. It gets infinitely large. So it's not going to work at -1. But what about when x is +1? What's 1 to any power? 1, right? So then we just get n. Does n converge as n goes to infinity? No, it doesn't go to 0 at all. So both of the endpoints fail again. All right. So we could just consider that. And now we know the endpoints fail again. We could just say, the interval of convergence, the IOC, is, or you could just say like this. You could say colon, and you could say x is -1 to 1. So it has the same interval as the original function. Try example 11 on your own. Very, very similar. Find a power series for the natural log of 1 minus x centered at 0. And your hint is, what's the antiderivative of that? Okay, try that on your own. Interval radius convergence, go. All right, let's see what we do. Find a power series for the natural log of 1 minus x centered at 0. That's a Maclaurin series. You can always do Taylor's rule. Call this f of x equals the natural log of 1 minus x The center's at 0. Then you could find the derivative, right? Let's review what that would be. The derivative of the natural log of something is 1 over the something times the chain rule. We won't get fooled again, said the who, times -1. And then you plug in the center, and that'll give you the numerator of your coefficient for the 0th term, for x to the 0. Bless you. So that the next column would be what's f prime of the center, which is 0, and that's -1 over 1, which is -1. So I know the first term is going to be -1 over 0 factorial times x minus 0 to the 0 power, or just -1, but it's going to be a negative number. So that might be pretty efficient. But if you're given a hint like this, or they might actually tell you on part B, hey, take the integral of this, and then on part C, now find a Taylor series for it, and you have to go, oh, that's the one I wanted. This is my geometric series. So let's try that over here. Here's option 2. The integral of 1 over 1 minus x dx. I told y'all you can always bring it to the top. That way it looks like a product. And now you have an inside function that's more than x. Its derivative is -1. Do we have a -1 out front? No. So now we're off by a -1. So we have a correction of its reciprocal, which is also -1. And now the rule of integration, right? When your inside function is in the numerator to the negative first, and you try the power rule, it'll fail, right? So who comes to the rescue? Natural log of the absolute value of 1 minus x, and then plus c. So the antiderivative is negative natural log of 1 minus x plus c. Now, I want to create a series for just the natural log of 1 minus x. So I should be able to do the following. I should be able to take the integral term by term down the line of the series for 1 over 1 minus x. And then like I was going to do in the previous problem when I forgot the chain rule, just multiply everything through by -1. Constant multiples can go at the end. So here we go. We'll say then that the natural log of 1 minus x, and we're going to see what values of x. It's centered at 0. So I'm sure that that's going to end up being, when we find the interval of convergence, we'll find values of x that work. It's going to be the integral, or we'll say this, the opposite of the integral of 1 over 1 minus x. Okay, it's the opposite. And now all I got to do is take the antiderivative of all the sides. So if you want at first, you could say 1 over 1 minus x. So you can see it, 1 plus x squared plus x cubed plus ... plus x to the n. It always helps to write them out first. And now you can essentially integrate both sides. Well, I already integrated that. I know I'm off by a negative. So let's just go down the line. What would be the antiderivative of 1? X, right? And then the antiderivative of the next term, 1/2 x squared, right? And then plus 1/3 x cubed. And the next one would be 1/4 x to the 4th plus ... plus. Now the nth term, x to the n plus 1 all over n plus 1 plus ... right? All we're doing is we're integrating the polynomial that represents it, and then plus ... and then plus c plus ... Well, I'll be doggone. Remember that plus c, we talked about it earlier when you're finding the general solution? That is a constant, right? And in Taylor series or Maclaurin series, we like to write things in increasing order. So the degree on a constant is 0. It's like cx to the 0. So where would be a better place to put it when we're doing these series? In the front, not the back. Yeah, in the front. Now, let's go ahead and I'm going to leave the negative out front, or I could bring the c to the front if I want. And I can either call it negative c or positive c, whatever. It doesn't really matter. But I'm going to bring this guy to the front. And I'm also going to distribute the negative. Minus x minus 1/2 x squared minus 1/3 x cubed minus ... minus x to the n plus 1 over n plus 1 minus ... You can do minus theirs, or you can still do pluses. It's okay, because addition is just adding the opposite. Okay, now there's one last thing I have to do. I need to know what c is. I need to know what c is. Was I given an initial condition?
Oh my God.
C equals 0? Well, that's a different C. Yeah, I'm glad you brought that up. The little c up here is the lowercase c. That's the center of the approximation. This is capital C, the constant.
We have no initial.
We don't, but I do know that the function and the series that it represents always, regardless of the radius or the interval, they always have the exact same slope and y value at the point of tangency, right? At the center. So at 0, if I can figure out what the natural log of 1 minus x is at the center, that should also be the value of the polynomial at 0 as well, right? So I can generate a point anytime by using the center. So let's go off to the side on our other, we got lots of workbench space here. We'll say at x equals 0, which is the center. I get the natural log of 1 minus 0, which is the natural log of 1, which is 0. So I know that 0, 0 has to satisfy, like a Snickers bar, both sides. So I can use that as an initial condition. All right. So what do I get when I plug it in? And I solve for C. I plug it into the left side, which is the natural log of 1 minus x. I get 0. And I plug in a 0 for x. What's going to happen with every single one of those terms? They're going to go away. And I get negative C equals 0, which means C equals 0. And I plug it in right there. And so I get the following answer. The natural log of 1 minus x is finally equal to negative x minus 1/2 x squared minus 1/3 x cubed. What would be the next term? I need 4 of them at least. X cubed, sorry. 1/4 x to the 4th, good. Plus dot 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 plus x to the n plus 1 over n plus 1 plus yada yada yada. Okay, they're all minus. Oh, it's, yeah, you could put plus or minus. It doesn't really matter. I mentioned that a little while ago. But yeah, certainly if you're going to put a minus, that would be okay. But make sure your dot dot dots don't look like minus signs then. There could be a little bit of confusion there. Okay. When you're not actually writing the specific next term, you could put plus or minus if you want. Just like when we do plus C, you could really put plus what? F or G or Q, whatever, but it's customary, you know? So that was a good one, right? Now we need to check the interval of convergence. If this is my rule of sequence right here, will that converge at all when x is, let's do the easy one first. When x is 1, because we know it centers at 0. We know the radius doesn't change. The radius is still 1, but we have to check the endpoints now. When x is 1, we get 1 to the n plus 1. What's 1 to the n plus 1? Just 1, right? And the negative we can leave out front. So we're left with just sigma 1 over n plus 1. Let's write that down. I see a lot of blanks there. We haven't tried out endpoints yet for a geometric series, but because we integrated, we have to check. So let's go ahead and write this out. The radius of convergence is still 1. So the possible interval of convergence, since the center is 0, would be negative 1 to 1 with brackets or parentheses. We'll put a question mark there. So let's go ahead and we'll check it out. We'll put test colon at x equals, I'm going to do 1 first because it's easier. We don't need colon there. Test at x equals 1. Okay. I'm going to plug it into here. That's going to be negative 1 to the n plus 1. That negative's up front like that, all over n plus 1. And there should be a sigma behind there. Remember, we do it on the sigma. I never collapsed it down to sigma. I'm just going to write sigma there because the intervals don't really matter. Now, again, 1 to any power is 1. So the top is always a negative 1. So you can actually factor the negative 1 out, and you're left with this right here. This is what happens when you plug in a 1. Does that series from 9.1 converge or diverge? Let's not forget what we learned in that section. It's 1 over n to the first. You would compare it to 1 over n to the first, right? Either by the direct comparison or limit comparison. And what do we know about sigma of 1 over n? It's your gatekeeper, right? That's your divergent harmonic series. So that one diverges, right? That diverges. So can we include the right endpoint of 1? No. So I'm going to come over here and I'm going to get rid of the beefy bracket. Can't include the beefy bracket. All right. So it's got to be open wimpy parenthesis. But look what happens when x is -1. Let's test that x equals -1, colon. We're going to get sigma, the negatives out front, and then we have a -1 to the n plus 1 all over n plus 1. Now that -1, that's right there. Again, it's just a constant multiple. So you could pull it out front if you want, like that. Well, that one doesn't simplify at all. This one is now an alternating series, right? Because you have the alternator in the top. So how do we do the alternating series? We cover up the alternator and we look what's left, 1 over n plus 1. Does the rule of sequence 1 over n plus 1 decrease to 0 as n goes to infinity? Yes, it does. So what can we say about x equals -1? It works. Yeah, it converges. Okay, converges. Yay. Alternating series test. And this one up here would diverge. So there you go. We did change the interval. We can come back up here now on our possible and get rid of the wimpy parentheses. So this one right here is your interval. Okay. So that kind of should make a little bit of sense to you. When we took the derivative, remember when we take the derivative, we kind of get rid of things, right? Constants go away. So neither endpoint was included. But when we integrate it, like we're going backwards, right? Well, now we have one of the endpoints showing up, working. Okay, so this would converge on the half open interval. All right, any comments or questions on that one? Geometric series. Let's look at a question that is similar to an oldie but a goodie from 2008. I kind of modified it a little bit. The sixth and final question on the BC exam on the free response, which is the very last question on the test. It's typically the sequence of series question. No calculator. All right. Let's knock this one out. All right. So part A, you're going to have, if you've been looking at any of the practice tests I've had up there, it's similar to this, but there's a box. You'll have a space to work in your test booklet. Write the first 4 non-zero terms and the general term for the Taylor series for f of x, which is 1 over 1 plus x squared, centered at 0. Okay. So what's the first thing you're going to do? You're going to be like, well, I'm just going to go ahead and generate my coefficients, the numerators of the coefficients, using Taylor's rule, right? Hopefully not. When it looks quotient-y like this, you might be able to build it from what you know. Let's see. Yeah, 1 over 1 plus x squared. Remember, I need to make it 1 over 1 minus something, right? And then this something is what I'm going to call my r. Well, we did this last 2 days ago, yes. Monday. How can I write minus x squared or plus x squared as a minus something? Negative x squared, right. Now, when you write it like that, the order of operations are important. That squares it first and then multiplies it by -1, right? It's not quantity negative x squared. So that should work. So this now tells you what you need to plug in to your desired series. So let's go ahead and write out our series that we know, 1 over 1 minus x, and that's just 1 plus x squared plus x cubed. It said the general term, so we'll write out plus or dot x to the nth power plus dot. So always write it down first and then create it underneath there. Let's just do the x squared first. Let's replace x with x squared. Or do you want to, let's do it with negative x squared. We can do this all in once. I think we can. So now we could say 1 over 1 plus x squared is going to equal, and all I got to do, and this is how I always do it, if you notice all year long, because I'm substituting in for x as I go through, whether it's sine, e, cosine, or this one, I always replace x first with receptacles, okay, with parentheses. And then all I got to do is come back in there, and whatever I've decided over here I need to plug in, I'll just go ahead and drop a negative x squared in everywhere. Negative x squared, negative x squared, negative x squared, negative x squared. Now, it doesn't say to simplify it, but it does say to write the first 4 non-zero terms and the general term. Do we have 4 non-zero terms? 1, 2, 3, 4. Boom. Yeah, we did. Let's go ahead and simplify just a little bit. That's going to be a 1, and then it's going to be a minus x squared. And then now, because we're squaring a negative 1 and an x squared, the negative is going to become positive, and then it's x to the 4th. And now we have a negative 1 cubed, which means that term is negative, and then it becomes x to the 6th. Okay, so it looks like it's becoming an alternating series, right? And it is. And if we had to generate the next term inherently, what would it be?
Negative x squared.
Would you say plus negative 8? Plus x to the 8th. Yeah. So I'll just put plus dot 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 plus. And now over here, again, you could separate this. You could say that that's negative 1 to the n times x to the 2n plus dot dot dot. That's kind of the nice way to separate it when it's alternating. Yeah. Okay, so there it is. There it is simplified. It did say to find the general term and the interval of convergence. So if you did want to collapse this down, we didn't do this on the other one, but you'd say from n equals 0 to infinity of negative 1 to the n times x to the 2n. And now you just need to make sure your starting value of n generates a 1. What would that need to be? Will we start at 1 or 0? It looks like 0, right? When I plug in a 0 for n, I get negative 1 to the 0, which is 1. And then I get x to the 0, which is 1. So yeah, I should start that at 0. You don't need to worry about the starting value until you collapse it down to sigma notation. All right, now let's go ahead and find the radius of convergence. This is a substitution one. So remember, to converge, we need the absolute value of r to be less than 1. Well, what is our r? We plugged in a negative x squared, right? And if I simplify that, that's like the absolute value of negative 1 times the absolute value of x squared. That's just the absolute value of x squared. And now I need to know for what values that is less than 1. Now we had one like this earlier. What was the solution set? Do you remember?
X is between the negative square way.
Yeah, it's hard when it's squared. You can't just like take the square root of both sides. So let's think about this one graphically. What does y equals x squared look like? Well, it looks like this. And we know it's already positive, so the absolute values aren't a big deal. I want to know for what values of x is that thing less than 1? Well, here's the y value of 1. What value of x do I need to plug in to each side to make sure I get a 1 or smaller? A 1, right? Or a negative 1, right? So if I plug in any value that is between negative 1 and 1, when I square it, that number is going to be between 0 and 1. So just like last time, it was the exact same. So the radius of convergence is 1, and because the center is 0, the interval of convergence is 0 minus 1 for negative 1, and then 0 plus 1, which is that. And what do? Do we need to test the endpoints here? No, we didn't take the derivative, we didn't integrate, so it's still negative 1 to 1. But you're welcome to like verify it for yourself right here. There's really no denominator. That's kind of what we need to make them converge. Okay. So that was part A in 2008. All right, now it says, does the series found in part A, when evaluated at 1, converge to f of 1? What does that mean? When the series converges to the function value, that means we're saying that the function value and the infinite series are the exact same, right? It's a perfect, on this interval from negative 1 to 1, it's a perfect evaluation. They always have the same number at the center, but we can drift left or right. But what about the endpoints? Is 1 included in the interval of convergence? It's not. So that's not going to work. So you'll say no. The series at x equals 1 does not equal f of 1 because, or since, x equals 1 is not in the interval of convergence found on part A, in part A. That's one way to do it. Okay. That's one way to do it. Or here's another way to do it. You could actually test it out. Let's test out x equals 1. Plug it into this series over here. Okay. So if I plug it into the rule of sequence, it would be sigma from n equals 0 to infinity of -1 to the n times, I'm plugging in a 1, 1 to the 2n. And now if I simplify that, what's 1 to the 2n power? It's just 1, right? 1 to any power. So this becomes -1 to the n. Is that alternator going to converge? No. You'll say diverges, which diverges. You could say by the nth term test. But again, the faster way is just to do what we did above. They're wanting you to realize that it's a modified geometric series. And unless you're taking the derivative or especially the integral, as we saw, you don't really need to test the endpoints. Okay. All right. So moving on, part C. The derivative of arctangent is 1 over 1 plus x squared. Oh, yeah, it is. I needed that for the multiple choice. Now, can I go back to the multiple choice and bubble that in? Because I needed it and I forgot it. No, you can't. But if it shows up on any one of the other 5 free response questions, you can go back to it. Like they're telling me something I already know. Thanks, College Board. Well, guess what? That's like what we just did. That's your hint. Okay. Write the first 4 non-zero terms of the Taylor series for arctangent centered at 0. Oh, okay. So I want arctangent, but arctangent is the derivative of 1 plus x squared. So if you want to write that out, it looks like this. The derivative with respect to x of arctangent of x is 1 over 1 plus x squared. So how can I use my Taylor series that I did for 1 plus x squared up above to get arctangent? Do I take its derivative or do I integrate it? If the derivative of arctangent is 1 over 1 plus x squared, then I'll say if, then the integral of 1 over 1 plus x squared with respect to x is arctangent of x plus capital C. I'm no fool, no siree. I'm going to live to be 103. I played safe for you and me because I'm no fool. All right. So we now have a plan. We're going to integrate what we did up here. So if you hadn't simplified already, this is where you'd want to go through and simplify. Oops. So let me just copy this down from up above. I don't know if that works. Nope. There we go. We're moving and grooving. Copy that, paste it down below here. That should be an equal sign. Okay. All right. Yeah. No, this is high powered stuff. And this is meticulousness, right? There's like little bitty details, so many terms. Okay. So if that is, again, that's the representation for 1. If you want to write that, that's 1 plus or 1 over 1 plus x squared. Let's integrate both sides. Okay. So I mapped out my plan over there. So now I'm going to say, so arctangent of x equals the integral of 1 over 1 plus x squared dx, which equals, let's just go ahead and start writing antiderivative terms. What could we put first if we're doing the antiderivative? Plus c, we can put it first, right? Okay, and now I'll integrate each term. The antiderivative 1 is x, so it's plus x minus 1/3 x cubed, and then plus 1/5 x to the 5th minus 1/7 x to the 7th. That's 4 non-zero terms. Plus dot 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 plus. Now, how am I going to integrate the general term? Well, we're going to have -1 to the something power. I can pull that out, but I can just do what I did over there. It's x to the 2n plus 1 divided by 2n plus 1, right? Add 1 and divide by the new exponent plus dot dot dot. Now, I do want to check to make sure that whatever value of n gives me an x, let's say, that it's the correct sign. It has to be positive. So in order to get an x there, n has to be what? 0, right? When n is 0, or when n is 0, I get x to the 0, which is 1 over 1. So would negative 1 to the 0 give me a positive term? It does. So I can just leave that as n. But I can't stop there because now I need to know what C is. They give me an initial condition to find C. Usually when they ask me to find the particular solution for an actual function, they give me an initial condition. They won't give you an initial condition here because, yeah, they gave me the function, and I know that it's going to be the same values for any value strictly between -1 and 1. So I can choose any x value I want between -1 and 1, and I can plug it into arctangent of x, and that y value will be my ordered pair. What do you want to choose? What's easy to evaluate between -1 and 1? 0, which is the center. Yeah. So we'll say when x equals 0, colon, I get arctangent of 0 to equal what? What is that arctangent of 0? Yeah, it's also 0 because tangent of 0 is 0. So again, it passes through the origin. So what do I get when I plug in a 0 for x? You can actually set it up then. So arctangent of x equals, or you can plug in a 0. So arctangent of 0, which is 0, equals c plus 0 minus 0 plus 0 minus 0. So guess what c is? 0. So, and now just like we do when we're solving differential equations, we plug that back into this version here, and we get our final answer. Arctangent of x is just x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th plus dot 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 plus -1 to the n times x to the 2n plus 1 all over 2n plus 1. Did it say to find the interval of convergence? No, but if it did, we would have to test -1 and 1 again. And to do that, we would need to collapse this down into sigma form. You don't need to collapse the general term down into sigma form if you put it in that plus dot 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 plus dot dot dot. But if you needed to, you could say or this equals sigma, and you just write that same thing again, x to the 2n plus 1 over 2n plus 1. And now you would say from n equals 0 to infinity. And now you have yourself a collapsed version that you could test. Let's just do it real quickly. Can we do this in our head? If you plug in a 1 for x, if you test the right endpoint at 1, you're going to get 1 to the 2n plus 1, which is 1, right? So you're going to be left with -1 to the n over 2n plus 1. This is bonus question right here. Okay, at x equals 1, you get sigma from n equals 0 to infinity of -1 to the n all over 2n plus 1. What does this one do? Intuition, alternating series test, right? So -1 to the n's an alternator, cover it up. What do we know about 1 over 2n plus 1? Does it converge to 0? Yes. So this is a convergent, conditionally convergent alternating series. Okay, what about at x equals -1? Now you plug it in for x and you get n equals 0 to infinity of -1 to the n. But now you're going to get -1 to the 2n plus 1 all over 2n plus 1. Is 2n plus -1 to the 2n plus 1, is that actually an alternator? Well, my gosh, I need to work on this a little bit. I don't know if this is going to work. Let's go ahead and combine exponents first of all, because it's -1 to the n times -1 to the 2n plus 1. I can add exponents. That's -1 to the 2n plus n is 3n plus 1. Holy crimoly. Is this an alternating series? I went from n equals infinity. That should be 0. If you're not sure, just expand it out for like the first 2 terms. If it, when n is 0, you get -1 to the first, which is a negative. When you plug in a 1, you get -1 to the -2th, or the 2th power. Now you get to the 4th power, which is an even, so it's positive. I'm sorry. No, when it's 0, it's what? You help me out. When it's 0, it's negative. When it's 1, it's positive. When it's 2 again, now it's 6 plus 1 is 7. It's negative. So it is an alternating. So can I include this endpoint? This is also a convergent alternating series. So I can include both endpoints. So for what it's worth, the radius of convergence is still 1, but the interval of convergence is now what? Beefy bracket 1 to 1 beefy bracket. And the reason we can do this is because, remember, what does the graph of arctangent of x look like? What's its domain? All real numbers all day long. Yes, yes, it is. Okay, so we don't have like obstacles to go on. So what we're saying, and you can verify this at lunch if you want, if this is -1 and this is +1, for infinitely many terms, the graph of the polynomial will perfectly duplicate the graph of arctangent of x. And then after that, the polynomial, like, nice knowing you, see ya, wouldn't want to be ya, or something. For infinitely many terms, that polynomial, and you can do, again, how would you verify that on your calculator? Just keep typing in these terms, as many as you feel comfortable doing, and then graph arctangent from like -2 to 2. Okay, we don't have time to do that, but it would look something like that. Okay, yeah, both endpoints work. Okay, and then the last thing right here, look at this. Use the series found in part C. Oh, I remember that series, right? Where is it? It's right here. There's so much stuff happening. There's the series right there. I still remember it. To find a rational number A such that the absolute value of A minus arctangent of 3/4 is less than 1/10. What the heck does that mean? Okay, let's decipher. Find a number A such that when you take that number and you subtract arctangent of 3/4 from it, you get a number, a tolerance that is within 1/10. Okay, I need some number minus arctangent of 3/4 to be less than 1/10. This is your alternating series remainder. Okay, and what we're doing, A ends up being the approximation of the sum, which we called S sub n. I need to find the sum so that when I take the approximation of the sum, A, minus the actual value of arctangent at x equals 3/4, it's within 1/10. So the first thing you need to notice is that because it's arctangent of 3/4, x is equal to 3/4. Okay, x is equal to 3/4. So let's go ahead and set up our series. Does it converge at 3/4?
Yes, it does.
Yeah, because that's within the beefy bracket -1 to 1. Here's what we're going to want to borrow. We're going to want to borrow this right here, the condensed version. All right, so let's come down here and write that. That's -1 to the n times x to the 2n plus 1 all over 2n plus 1. And now I'm going to go below there. Okay, I should write this below there. Now, when x equals 3/4, look what we get. N equals 0 to infinity of -1 to the n times 3/4 to the 2n plus 1 all over 2n plus 1. When I find the sum, I want the error. That's what this is. This is called the error, right? Because A would be the approximation. And then arctangent 3/4 would be the actual. We don't care if it's positive or negative. We take the absolute value. And that's the difference, right? That's the difference or the error. Because we want it to be less than 1/10, that's why we call it an error bound. Or remember, for the alternating series, the error has to be within the first unused term. Remember that? So there's a little bit of work here. It's the last one. I need to find for what value of n does this, the absolute value of it, give me a number that's smaller than 1/10. And remember, because it's the absolute value, let's just try it out. Let's just try n equals 1. We're probably going to have to go more than one term, right? When n equals 1, we get a sub 1, or the absolute value of a sub 1. What would the first term be when n is 1? It would be 3/4 to the 2 plus 1 is 3, right? All over 3. And this is a no calculator. So that's, wow, that's 27 all over 3. And then you can put the 64. That's 4 cubed down there. Is that less than a tenth? Oh, well, let's simplify. That's the same as 9/64. Is that less than 1/10? No, that's not less than a tenth. No. So let's try n equals 2. The absolute value of the second term is going to be, and again, you don't have to worry about the alternator because it's absolute value. It's going to be 3/4. To the plug in a 2, you get 4 plus 1 to the 5th, all over 2 times 2, which is 4 plus 1 is 5. Wow, that becomes 3 to the 5th, all over 4 to the 5th, with a 5 in the denominator. Now, you can kick the 3/4 off to the side to the 5th, and then leave the 5 down there. Are they expecting us to simplify that? I mean, do we have to really multiply that out? Yikes. Is that going to be less than a tenth?
Yeah.
Well, let's see. If I compare it to a tenth, let's see. I'll put less than a tenth with a question mark. To make a 1/10, you can kind of match it up like this if you're not sure. Let's multiply by 3 to the 5th over 3 to the 5th. All right, that's legal, right? So now I have the numerators matched up. So now I can just compare denominators. The only way it's going to be less than the number on the right, now that the numerators are the same, is if the denominators are what? Yeah, if the denominator is bigger. So is 5 times 4 to the 5th bigger than 10 times 3 to the 5th? See how I reduce? Is 5 times 4 to the 5th bigger than 10 times 3 to the 5th? Well, we could divide both sides by 5. That works. So now you have is 4 to the 5th greater than 2 times 3 to the 5th. Yes, big time, right? It's pretty obvious at that point. So that's just like nuanced analysis. That's like that knows what's going on. So what does that mean? That means that n equals 2. This must be your first unused term, right? Which is kind of silly. It's the second term. So if the second term is my first unused term, how many terms am I going to add up? 1. So here's what we're going to say. So A, which I'm going to call S sub 1, it's the partial sum of the first 1th terms. So what do I get when I plug in a 1 for n? Well, I already did that, right? It's 9/64. But is it positive or negative? I do need to worry about that. So when I plug a 1 into the rule of sequence, what do I get? -1 to the 1th is negative, right? I didn't need to include them when I was doing the error, but now because I want the sum, I need to actually plug an n equals 1 back in way up here. Oh, actually, it starts at 0, doesn't it? Oops, my bad. It starts at 0. So I need that term as well. So that's going to be what?
1.
X is equal to 3/4. So I didn't do that over here. Let's do when n equals 0. I didn't do that. The 0th term, X is 3/4 still. So it's going to be 3/4 to the 0 times 2 is 0 plus 1th power, all over 0 times 2 is 0 plus 1th power. So it's 3/4, yeah. So it's positive 3/4. There you go, minus 9/64. And there you go. That's the answer. I don't like that negative there. So it was a simple idea, right? We know that for the partial sum, which they're calling A here, to be within a certain margin, I need to figure out when the absolute value of the first unused term is less than a tenth. And trust me, without a calculator, they're not going to make it like the 4th or the 5th term, right? But if you had a calculator, you can do it a lot more quickly. And remember, you don't have to worry about the alternator because we're just talking about error bound. Now, would we have to simplify 3/4 minus 9/64? Heavens, no. So is this now we would be done with the test and we'd be like, thank goodness, right? Because that was a burner, that was a brain burner, right? Details, tediousness, but that was an actual question that required you to use the geometric series test, okay? All right, now, and because it was an alternating series, we could use the alternating series test for the error. Okay, so when 2 Mondays from last Monday comes, that's the 9th, and you're on the AP exam, don't ever give up on something. I know right now Everything is coming together. And like, I thought I understood series until this section, right? You just got to sit down and make sense of it all. It's very tedious. There's a lot of paying very careful attention, but you could do it. I mean, the ideas are really the same. There's a little bit of memorization and then some mechanics that go along. You have to get proficient. So that's where the worksheet comes in. All right, now we didn't finish today, and that's okay. It's a really nice point to stop, and we'll pick up with 13 tomorrow. We know we can find exact values of geometric series that converge, and tomorrow we'll add to that. Thanks for paying attention to the bitter end, Ethan. Nice. Okay, great. He still doesn't hear me.
And every time I try to get a 5,
You can